difference equations in this standard form, which is usually called by the standard form for applying the averaging method. Okay, so it's given by x prime equals to epsilon multiplied by a function. T is the time variable where I'm taking the derivative. Prime denotes the derivative with respect to t. X is the spatial variable, and epsilon is a distinguished parameter, which is the parameter of perturbation. Of course, the difference equation can have a lot of parameters, but we need a distinguished one, which will be the small parameter. Okay, so the domain of the difference equation is given by r times d times minus epsilon 0, where d is an open-bounded set of Rn, and epsilon is a positive parameter, which is assumed to be small. Okay, so in order to avoid any problems in the boundary of the domain, we assume that all the functions, that the function of the right-hand side of the difference equation is continuous also on the boundary of D. Okay, so f is a continuous, at least a continuous function on R times the closure of D times minus epsilon. It's usually to have this function f given as power series of epsilon up to some order k. So in this case, fi is the coefficient in this power series of epsilon power 2i, and r is just the remainder of high order terms of epsilon. Okay, so it always comes with an epsilon k plus 1 multiplying before the function. Okay, so we are going to also assume that this difference equation is t periodic in the variable t. Okay, so this is a basic assumption that we are going to do here. And for this lecture, for just today, we are going to assume that this function f is sufficiently smooth. Okay, just for the sake of simplicity, in order to do the computation. So we are going to assume just for today that this function is sufficiently smooth. Okay, so the first thing I would like you to notice about this difference equation is that the unperturbed system, and by the unperturbed system I mean the differential equation 1 for epsilon equal to 0, because epsilon is the parameter of perturbation. So unperturbed system is when I put epsilon equal to 0. So notes that all the solutions of the unperturbed system, in this case x prime equals 0, it's the trivial one, the solutions are the constant ones. Okay, so we have here the time variable, here the spatial variable. Let's just indicate here the open set D. Okay, the domain of our difference equation. And for the unperturbed system, for each initial condition that I take in the domain, the solution passing through these initial conditions is the constant one. Okay, for every initial condition. So we can see these solutions as being t-periodic. Okay, I have t. So all the solutions of the unperturbed system are t-periodic functions. Okay, so the main idea, the main goal of this course is to explore conditions on the perturbation in order that some of these periodic solutions persists as periodic solutions when epsilon is distinct from 0 but small. Okay, so we have for the unperturbed system all the solutions periodic. When epsilon is distinct from 0, can I detect any periodic solutions? Some of the periodic solutions persists. So that is the main goal of this course. Investigate conditions on the perturbations in order to have some periodic solutions when epsilon is distinct from 0. Okay, so the first result, let's start from the very beginning. Okay, so the first result about this differential equation is just a consequence of the Picard-Lindelof existence and uniqueness theorem for differential equations. So the result is the following: there exists an epsilon bar. Okay, of course it's less, it's smaller than epsilon 0, such that for each initial condition, the difference equation 1 admits a unique maximal solution, okay, satisfying x of 0 equal z. So this function denotes a solution of the difference equation 1 such that for t equals 0, it returns the initial condition of the solution. Okay, so this is the Picard-Lindelof theorem about the uniqueness of solution. This interval, EZ of epsilon, denotes the maximal interval of definition of the solution. It's always an open set. And in addition, this epsilon bar can be taken sufficiently small in order that this closed set 0t is contained in this open maximal interval of definition. Okay, so here, let me just copy this graph. What I'm saying is that for each initial condition inside D, I know that if epsilon is inside this closed set minus epsilon bar, then the solution is starting at this point is defined at least for t equal the period of the difference equation. Okay, so capital T. Then is that what we have? We have the solution of the perturbed system defined for times which is bigger than t, because 0t is a closed interval inside an open set. So we can always take, for each initial condition, we can always take a time which is strictly bigger than t. And analogously, here we also have defined the solution for times smaller than 0. Okay, and this is important because since I want to study T-periodic solution, the first thing that I have to have is that I should be able to compute the solutions in the period. Okay, so the second classical result I want to show is a characterization of periodic solutions for difference equations like the difference equation 1. Okay, so a solution of a difference equation is periodic if x of t plus t z epsilon is equal to xt z epsilon for every t in the interval of definition. Let's assume that it's R. Okay, so this is what I have to check in order to prove that a solution of the difference equation is periodic. This theorem is saying that it's sufficient to check that for t equal the period, the solution coincides with the initial condition. We do not have actually to check for every t in the interval of definition. We just have to check these for t equal the period. Okay, so in order to prove this result, it's simple. It's the classical approach. This is a question. Okay, so I want to know if this is true. So we call this function by another letter, for instance, C, and you would just have to check if C satisfies the same initial problem that x, t, z, epsilon satisfies. Okay, so first we compute the derivative of C. It's just the derivative of x, t plus t, z, epsilon, so it's equal to, since x is the solution, is a solution of our difference equation, then it's just f of t plus t of x, t plus t, z, epsilon, epsilon. And now I use the information. F is t periodic in the first variable. So this is equal to f of t, and x, t plus t, z, epsilon is our function kc. So it's kc, epsilon. So kc is also a solution of the difference equation 1. Now I have to check the initial condition in order to see what is the initial problem that C is a solution. So C of 0 is equal to x of t, z, epsilon, and by hypothesis, it's equal to z. Okay, so C and x satisfies the same initial condition. Then by the uniqueness property, we conclude that x, t, z, epsilon is equal to Kc of t, which is equal to xt plus capital T, z, epsilon. Okay, so this theorem, this characterization of periodic solutions of periodic difference equations provides a first approach to investigate the periodic solutions. This approach I'm calling displacement function approach. So this relationship allows me to introduce the displacement function. It's just the time t map minus the identity. So this map here is called time t map, or in some places it can also be a Poincaré map. Okay, so the time t, the displacement function is defined as the time t map minus the identity. So it's x of t, capital T, z, epsilon minus z. Okay, so the idea here is to associate periodic solutions of our difference equation with zeros of a specific function, in this case, the displacement function. So what's happening here is that I'm trying, let me place here again. This is our basic picture. So I want to, if I consider an initial condition and I flow it by the trajectory, trajectory of our difference equation, then the displacement, this is x of t, z, epsilon, this is z, and this is also z, because this trajectory is constant, it's just a straight line. Okay? Then the displacement function is the difference between these two positions. It's equal to xt, z, epsilon, minus z. So when I have a zero of the displacement function, what I'm saying is that this solution starts at z and ends at z. And since our difference equation is periodic, then by this very same argument, we concluded that it corresponds to a periodic function of our difference equation. Okay? So with the displacement function, I can associate periodic solutions of a difference equation with zeros of a function. Okay, then it's could be more simple for investigating. Okay, instead of looking for periodic solutions or solutions of a difference equation that we know it's a hard task to do, we can now study zeros of a function. Okay. In this context, the stability of the periodic orbits eventually given by zeros of displacement function, the stability of this periodic solution can also be investigated using the displacement function. Okay, so when we have, suppose that we have a branch of zeros of the displacement function, that is delta z epsilon, epsilon equals 0 for epsilon closer to 0. Then for each epsilon close to 0, we have an initial condition that gives a periodic solution. Okay, since I have a periodic solution, we can define the Poincaré map around this periodic solution. And we know that the stability of the periodic solution is characterized by the stability of the fixed point of the associated Poincaré map. Okay, and in this case, since we have a periodic solution, the Poincaré map is just the time t map. Okay, so and of course, in this case, the Poincaré map is given by the identity now plus the displacement function. We shall see that the displacement function in this case is of order epsilon. That means we can always have an epsilon that multiplies another function. Let's call delta small delta. Okay, so in order to investigate the stability of the fixed point of the Poincaré map, a first thing that we can do is to look for the linearization of the Poincaré map. Basically, compute the Jacobian of the Poincaré map and study the eigenvalues of the Poincaré map. So, in this situation, when we compute the derivative of the Poincaré map at the fixed point, derivative with respect to the spatial variable, okay? At the fixed point, what we have is the identity matrix, okay, plus epsilon multiplied by the derivative of delta with respect to the spatial variable at z epsilon epsilon. So let's call this matrix by m of epsilon. It's just the identity plus epsilon times m of epsilon. So the derivative of the Poincaré map is given as a perturbation of the identity. Okay, so the eigenvalues of this matrix, the derivative of the Poincaré map, can be studied by means of the eigenvalues of the derivative of the displacement function. Okay, so in this situation, we know that if lambda epsilon is an eigenvalue of n epsilon, okay, then 1 plus epsilon lambda epsilon is an eigenvalue of the Jacobian of the Poincaré map at z epsilon epsilon. Okay, so if we have a hyperbolic fixed point of the Poincaré map, which is a hyperbolic fixed point, it's a fixed point such that the eigenvalues of this matrix has a modulus distant from 1. Okay, the modulus of every eigenvalue is distant from 1. So if we have these, then we can characterize the stability of this fixed point by means of eigenspaces, etc. Exactly, stable invariant space, unstable invariant space. We can do this. We can perform this decomposition. Okay, so this is the property for the eigenvalues of the Poincaré map. Okay, but if we have the eigenvalues of this matrix N, then we can do the same characterization, but now looking at to the eigenvalues of the matrix M epsilon. Why? Because the norm of lambda, the modulus of lambda square is just 1 plus epsilon times the real part of lambda epsilon plus order epsilon squared. Okay, so if for instance the real part of lambda 0 is positive, the real part of lambda 0 is positive, then the modulus of lambda epsilon squared is, oh, we can take off the square, is greater than 1 for epsilon sufficiently small. And if the real part of lambda 0 is negative, then just looking at this relationship, then the modulus of lambda epsilon is smaller than 1 for epsilon sufficiently small. So I'm not going into much details about the stability of the product solutions given by averaging method, for instance, but we can always do something in order to investigate this stability. Okay, and this is always the main idea, to use the displacement function in order to approximate and to estimate the eigenvalues of the Jacobian of the Poincaré. Okay, this is the idea. In this very simple case, we can establish if a periodic solution is asymptotically stable. Okay, this situation is asymptotically stable, and the situation is unstable. Okay, well, this is the first approach that we are going to follow and use in this first lecture. There's another approach which is more suitable for context with less regularity. It's the operator equation approach. I have some references where it's used and developed. So the basic idea of this approach is to use the integral characterization for solutions of differential equation. Okay, so if x of t is a solution of x prime equal epsilon ft x epsilon. Okay, so let me just set it better. X, a continuous function between 0 and t are n, sorry, is a solution of this differential equation if and only if it satisfies the following integral equation: xt equal x of 0 plus the integral between 0 and t of epsilon f of s x of s epsilon ds. Okay, so this is a simple characterization of solutions of differential equation. Okay, this is always true. We can do the same now. Let's just put x of 0 on the left-hand side of the equation. So this is equivalent to say that x t minus x0 is equal to the integral of 0 between 0 and t epsilon f s x s epsilon ds. So here we can define a linear operator. Let's call this difference by L applied to a continuous function x evaluated at t. And in the right-hand side of this relationship, we have n epsilon. Let's define this nonlinear operator. N epsilon of x evaluated at t. Okay, so L applied in a function x is another function given by x of t minus x of 0. This is another function, a new function. Okay, so L is an operator from the continuous, from the set of continuous function onto the set of continuous function. Okay, and this is another operator which associated a function, a continuous function x to another function which is given by this integral. Okay, so here we have a characterization of a solution of a difference equation. X, a continuous function, is a solution of the difference equation if and only if L applied to x is equal n epsilon of x. Okay, so this is called an operator equation. Okay, so it's controlling when a function, a continuous function, is a solution of a difference equation. Okay, but it's not giving any information about the periodicity of the solution. It's just saying that if this happens, then x is a solution of the difference equation. Then in order to investigate the periodic solutions of the difference equation, we just have to state suitable spaces where these operators are defined. So that's what I'm going to do right now. So let us define it, x as being the set of continuous functions, just like these ones, such that x of 0 is equal x of t. I'm not assuming that those functions are periodic because it's only defined in the interval. Okay, it's only defined in the interval. But we have the property that if a solution coincides for 0 and for t, then it can be continuously extended to a periodic solution. Okay, so if we find, for instance, a solution for this operator equation inside the set, then it can be continuously extended to a periodic solution of the difference equation. And that is the key for using this approach. Okay, so just to state, because I'm going to use it in the next class. Okay, so X is the set, is a blank space of the continuous function such that x of 0 is equal x of t, and y is the contour domain. Okay, because the image of a function by L always has the property that for t equals 0, it's 0. Okay, so that's the space y, the set of continuous functions such that x of 0 is equals 0. So x and y are blank space with the subnorm, etc. The idea here is to find periodic solutions inside a set of the domain. So given a set, an open set V of Rn such that the closure of V is inside in the domain, we denote this another set omega, which is a subset of X, okay, such that X of t belongs to V for every t in the domain of definition of X. Okay, so this is the set of continuous functions such that x of 0 is equal to x of t, and such that x of t is in V for every t between 0 and capital T. Okay, so it can be seen to be an open-bounded subset of capital X. And in this set, we define this linear map that I have introduced before, but now defined in a smaller space. Okay, so L of x evaluated at a t is equal to x of t minus x of 0. Okay, and also we introduce now this nonlinear this nonlinear map, but now define it in the closure of omega, which is given by the integral between 0 and t of epsilon f s x of s epsilon ds. It's just the integral. And the theorem 4 that characterizes these approaches says that a function x in the space capital X can be continuously extended to a t-periodic solution of the differential equation 1 inside the closure of V if and only if it's a solution of the operator equation. Okay, then we can use tools from functional analysis, for instance, in order to study this operator equation and try to find solutions of this operation equation. It's going to appear in the next class, but it's nice to have these two distinct approaches for investigating periodic solutions in mind. Okay, so now let's start talking about the averaging method. How can we use, what is the averaging method? How can we use the averaging method to investigate periodic solutions of different equations given in the standard form? Okay, so the idea of the averaging method is provide asymptotic estimates for the solutions of difference equation 1 in terms of solutions of an autonomous difference equation. Okay, so this is very important because it's very important to note that the difference equation, the standard difference equation that we are considering, is non-autonomous. Okay, it's non-autonomous. We have to have this in mind because if not, we could try to apply the averaging method for vector fields, for instance, for autonomous difference equation. And in this case, the solutions, the periodic solutions that we eventually find are not actually periodic solutions, but critical points. Okay, so it's important to have in mind that I'm going to talk about non-autonomous difference equation. And the idea of the non-autonomous, the idea of the averaging method is to approximate the solutions of a non-autonomous difference equation by solutions of an autonomous difference equation. So it's clear why the standard form is non-autonomous, because if it's autonomous, there's nothing to do. Okay, so the idea of the averaging method is to approximate solution of a non-autonomous difference equation by solutions of an autonomous difference equation given given this form. So it's not well defined yet what are those GIs, but this system will be called truncated averaged equation, and the result that gives this approximation is this result. This is the averaging result. Okay, so let C be the solution of 4 satisfying that the initial condition of the solution is Z. Okay, so C of 0, Z epsilon is equal to Z. Then the result is the following: there exists an epsilon hat positive such that the norm of the difference between the solution x t z epsilon, that is the solution of the difference equation 1, minus the difference between this solution and the solution of this truncated average equation, is of order epsilon power k. Okay, for every t belong to this interval 0 L divided by epsilon. So when epsilon goes to 0, this difference goes to 0, and this interval, okay, the length of this interval goes to infinity. Okay, and this is true for every epsilon inside minus epsilon hat, and for some fixed L positive. Okay, so I'm aware that I haven't defined this function yet, but this is the averaging result. Okay, this is the averaging theory, the main theory of the averaging, the main theorem of the averaging theory. Okay, so we approximate solution of an non-autonomous difference equation by solutions of an autonomous difference equation. And how can we find these functions, okay, these GIs that makes the theorem 5 true? So it's obtained by this theorem. Here I'm indicating the reference where these theorems can be found, okay? So it's a len, and the function gi can be computed by doing change of coordinates. So this is the result. There exists a smooth t-periodic near-identity transformation given by x equal an u t c epsilon. This function, this transformation, is a near-identity transformation. This means that this is the identity x c plus epsilon times something. Okay, in this case, since we are working in another k scenario, remember that our standard form is given in power series up to order k. So here we consider also a transformation which is near identity transformation, but we have perturbations up to order k. Okay, so there exists this transformation satisfying the so-called stroboscopic condition. I'm going to comment this condition in a second. Satisfying the stroboscopic condition, that is, u of 0 xc epsilon is equal xc, does not depend on epsilon, such that the difference equation 1, our standard form, is transformed into this new differential equation. So notice what's happening here. This transformation removes the dependence of the variable t of the standard form from the order k approximation. Okay, so the dependence of t does not appear in the transformed system up to order k in epsilon. Okay, and the dependence on t appears now in the remainder. And in this case is arbitrary. Okay, we can do, we say that we do a first order analysis if I remove this dependence from the first order coefficient. A second order analysis, I can remove the dependence on t from the first and second coefficients of powers of epsilon. Okay, and so on. We can do these recursively. Okay, so an important information about the stroboscopic condition. The stroboscopic condition provides, let me write here, the stroboscopic condition provides the uniqueness, sorry, this is my sister, provides the uniqueness of the functions ui and gi. In order to have this conjugation, we do not need to assume the stroboscopic condition. But if you do not need, if you not assume the stroboscopic condition, we do not have uniqueness of the functions gi. Okay, you have several possible choices for doing this conjugation. If we assume the stroboscopic condition, or there is a lot of conditions that implies the uniqueness of this function, then it is completely well defined. Okay. Right. Another comment about the stroboscopic condition. The stroboscopic condition now plus the periodicity, the t-periodicity of u implies that the transformation u of n t kc epsilon is equal kc for every n for every integer n. Okay, that's why it's called stroboscopic. Okay, so note that if x and c are the solutions of the difference equation, the standard form 1 and the truncated averaged equation, this, okay, then by the conjugation provided by theorem 6, we have that x t z epsilon is actually equal to u t c t z epsilon epsilon. Okay, so let's see why this is true. We know that if we define it xt equal u t c t z epsilon epsilon, it is actually a solution of the difference equation 1, because theorem 6 is providing a transformation of the difference equation. Okay, so this is the solution of the transformed difference equation, and I'm applying the transformation, and I'm going back to the initial difference equation. So here we have that x prime of t is actually equal to ft of x t epsilon. And the initial condition is equal to y of 0, kc 0 z epsilon, epsilon, it's equal to u of 0, kc 0 z epsilon, by definition, is equal to z. And now, from the stroboscopic condition, it's equal to z, okay? U 0 z epsilon is equal to z. Then we have that this x and this x of t z epsilon satisfies the same initial problem. So xt is actually xt z epsilon. Okay, this means that if we study the differential equation 5 and we discover an initial condition such that the solution of the differential system 5 is t periodic, then for this same initial condition, the solution of the original difference equation, the standard one, is also t periodic. Okay, so instead of studying directly the periodic solutions of our standard form, the difference equation 1, we can study periodic solutions of this transformed differential equation. Okay, so this is what I'm saying here. Xtz epsilon is t periodic if and only if the solution kctz epsilon is t periodic. Okay, so we can change the system that we are studying. Okay, so but so far I did not show the expression of these functions. Okay, so let me show how to obtain the first one, G1, and the other ones follows an analogous procedure. Okay, so how can we obtain the first order average function? We are going to call this first order average function. It's going to be clear enough. So by the previous theorems, we know that this difference equation is conjugated to this difference equation through this change of coordination, this transformation, change of variables. Okay, so we have that those difference equations are conjugate to each other through this transformation. Okay, so denoting xt equal the solution of the difference equation 1 and ct the solution of the difference equation 5, the previous remark implies that xt is equal to kct plus epsilon u1 t kct. Okay, it's exactly what I'm saying here, but using now the expression for u. So computing the derivative of x, we have by one hand that the derivative of x using this relationship is equal to the derivative of c plus epsilon multiplied by the derivative of u with respect to the variable t. So when I compute this derivative, we get the derivative of u with respect to the first coordinate plus the derivative of u1 with respect to the second coordinate multiplied by the derivative of Kc. We know that Kc is a solution of this difference equation. Then we can make the substitution. I'm not going to read all of that, but after substituting the expression for the derivative of x of c, what I'm doing here now is collecting the coefficients of epsilon. So this is equal to epsilon multiplied by g1 of c of t plus the derivative of u1 with respect to the first variable evaluated at t ect. Okay, and other, we have several other terms here, but it all of them have power of epsilon squared or higher terms. Okay, so this is the derivative of x by one hand. On the other hand, we know that x is a solution of the original differential equation 1, so we can compute its derivative using the standard form. So the derivative of x is equal to epsilon multiplied by f1 of t xt plus the remainder. Okay, now substituting the expression of xt, this one, we have this epsilon times f1 of t, the value of x of t through the conjugation plus higher order terms. Okay, so everything here is smooth, so we can, for instance, consider the Taylor expansion here and check that f1 c t plus order epsilon, that's what we have here, is equal to f1 t ct plus order epsilon. Okay, so this is what we get. X prime t is equal to epsilon times f1 dt ct plus order of epsilon e squared. Comparing this expression for the derivative of x and this expression for the derivative of x, we, since they must coincide for every epsilon, we have that this coefficient coincides with these coefficients. So the function u1 must satisfy the following homological equation. The derivative of u1 with respect to the first coordinate has to be equal to f1 of t c minus g1 of c. That's what we have here. This is called the homological equation, and the others functions, higher order functions, u, I, and gi, also obey homological equations. So in order to compute the other functions provided by theorems, by the private theorems, we have to compute recursively solutions of homological equations. Okay, so in this case, just for the first one, we can integrate this homological equation and conclude that u1 is equal to the integral between 0 and t of this difference plus a function which does not depend on t. Okay, it just depends on Kc. And for averaging, do not assume in the stroboscopic conditions, is exactly this kind of function that breaks the unicity of the possibility for u and g. Okay, so since the transformation is t-periodic in particular, we have u1 of t equal u0, u1 of 0 equal h1 of c. We conclude that the integral of this difference has to be 0. Okay, just to substitute here and see that it has to be 0. And from this relationship, we get the expression of the first order average function, which is actually the first, the average. This is the average of f1 as kc. Okay, I mean, what I'm doing here is integrating a t-periodic function in its domain of the first domain of the first interval periodicity and divided by the period. So this is the average of function f1. Okay, so going back to this relationship, we can compute now the expression for the transformation. u1 is equal to this integral. Okay, so the averaging method is telling me that using this transformation, actually this one, we can approximate the solutions of the original difference equation by the solutions of a truncated average equation. Okay, in this case, x dot x prime equal to epsilon 1 divided by t integral of between 0 and t f1 as kc ds. Okay, so this is an autonomous difference equation. It's a vector field, and it approximates in terms of these theorems the solutions of the solution of the standard form, this one. Okay, so how can I use these informations in order to investigate periodic solutions of this difference equation? Okay, by remark 7, we know that periodic solutions with a certain initial condition of this difference equation coincide with the initial condition. For the same initial condition, the solution of this difference equation will also be periodic. So what I'm going to do is to study the displacement function of this periodic of this difference equation. That's what I'm going to do here. So we consider this difference equation.
Douglas, let's do a break.
Okay. Let's do a break.
You change the section.
Okay.
Okay, let's do a 10 minutes break and return soon. Any questions for Douglas anyway? Okay, 10 minutes. Thank you, Douglas.
Thank you. So
let's continue, Douglas.
Let's continue. Okay. As I have showed, the averaging theorem allows us to conjugate the solutions of this difference equation with solutions of these difference equations, okay? And keeping the initial condition, right? Now, in order to use this information, in order to study the periodic solutions, what I'm going to do is to compute the displacement function of the transformed system, okay? Recall that now we have a expression for G1 as CTS, okay? So, in order to compute or estimate the displacement function of this differential equation, we use again the integral characterization of solutions of differential equation. Okay, so Kc of Tz epsilon is equal to z plus the integral of the right-hand side of the differential equation computed at the solution. Okay, so this is equal to the integral between 0 and t of epsilon g1 of the solution plus epsilon squared r1 of the solution. I computed as the solution. Okay. Using that g1 composite or evaluated at the solution is equal to g1 of z plus order epsilon. This is again a Taylor expansion of this function around the epsilon equals 0. We can substitute this here and conclude that the solution, Kc, writes like z plus epsilon multiplied by the integral of g1. G1 does not depend on t, it's autonomous, the first order. So we can compute explicitly this integral, this is just z plus epsilon t g1 of z, and all the remainder is of order 2 in epsilon. Okay, so this is the integral of something which is bounded in epsilon plus the remainder. Everything is continuous. The solutions is defined in a compact because when I computed the displacement function, I just take t equal capital T. So this can be bounded by a constant. So this remainder is just an order of epsilon squared. So the displacement function is given by epsilon capital T g1 of z plus order epsilon e squared. Thus, defining another function, delta tilde, by dividing the displacement function by epsilon, we get t multiplied by g1 of z plus order of epsilon. Thus, if z star, a point in the domain, the spatial domain, is a simple zero of g1 of the first order average function, then what we get is that delta tilde of z star 0, it vanishes. Then we have g1 of z star, which also vanishes because I'm assuming that z star is a 0 of g1, then it's equal to 0. And the determinant of the differential of delta tilde with respect to the variable z evaluated at z star 0 is distinct from 0 because it's exactly t multiplied by the derivative of g1 evaluated at z star. And we know, because it's a simple zero of g1, that this determinant is distinct from 0. Then we can use the implicit function theorem to obtain the existence of a unique function z epsilon defined in a neighborhood of epsilon equals 0, neighborhood E, satisfying z of 0 equals to z star and delta tilde of z epsilon equals 0 for every epsilon in I. This implies also that the displacement function applied in z epsilon is equal to 0 for every epsilon in y, in I. Okay? So, taking theorem 3 into account, we know that this function is a t-periodic solution of this difference equation, because I find a branch of zeros of the displacement function, and we know that zeros of the displacement functions corresponds to a periodic solution of the differential equation. And now, taking remark 7 into account, we know that the solution of the difference equation 1, or this one, which has less orders, the solution of this difference equation with the same initial condition, z epsilon, is also t-periodic. Then we find a t-periodic solution of our original difference equation. And this t-periodic solution also satisfies that it converges to a constant function z star as epsilon goes to 0, because the initial condition goes to z star, and the solutions of the imperturbable system are all constant solutions. Okay, so with these comments, we have proved this theorem, which is the first order averaging theorem. We usually call it as first order averaging theorem. Assume that z star in the domain is a simple zero of g1, then for epsilon distinct from 0, sufficiently small, the difference equation 5 and consequently the difference equation 1 admits a unique t-periodic solution phi t epsilon such that it converges to z star as epsilon goes to 0. Okay, admits a unique t-periodic solution satisfying this property. Okay, so how about high order averaged functions? So so I'm using the averaging method, I'm computing G1, and the expression of G1 is exactly the average of F1. So since GIs are uniquely defined by the stroboscopic condition, it seems natural to call these functions by higher order averaged functions. Okay, so these functions GI obtained by an analogous procedure and solving recursively a sequence of homological equations, or call it higher order average function or average function of order I. Okay, I refer this function by stroboscopic average function because here we are assuming the stroboscopic condition. Eventually, if another condition is assumed, then this expression could be different. So I'm calling these functions by stroboscopic average functions, or stroboscopic average function of order I for GI. So I think that these I have already commented. Okay, so I'm not going to repeat the procedure of homological equations to find expression for these functions GI. We are going to have an expression for these functions, but at the end of the lecture. So assuming that I know now these functions, because I know that these functions exist, how can I use them to study periodic solutions of the difference equation 1? Okay, so these theorems, which are very analogous to the previous ones, also holds for higher order averaged functions. So denote G0 by 0, just for the sake of simplicity, and let L be the index of the first non-vanishing averaged function. Okay, we have our difference equation, the standard form. We can compute the first order average function, and it could be identically 0. Then we go to the second order average function. It could also be identically 0. We can do this procedure until we find a first order of average function that is not identical to 0. So L indicates this index. Okay, so L is an integer between 1 and k, satisfying that G0 up to GL minus 1 is equal to 0, and GL is not identically 0. And the same result as before. Assume that Z star is a point in the domain such that it's a simple 0 of the first non-vanishing averaged function. Then, for epsilon distinct from 0, sufficiently small, the difference equation 5 and consequently the difference equation 1 admits a unique t-periodic solution phi t epsilon, satisfying that it converges to the constant function z star as epsilon goes to 0. The idea of the proof is the same. Use the implicit function theorem. So, implicit function theorem for the displacement function of the transformed system. Okay, so we consider Xi a solution of this difference equation, which is the transformed system, and we know that this difference equation, a solution of this difference equation, satisfies the integral characterization. Okay, so Kc of Tz epsilon is equal to the initial condition plus the integral between 0 and t of the right-hand side of the difference equation applied in the solution. Assuming that G0 up to GL minus 1 are all equal 0, we have that this expression, this relationship, reduced to this other one. So here I have sum of the averaged functions computed in the solution. If up to L minus 1 it's identically 0, then it goes away, it vanishes. So Tz epsilon is equal z plus epsilon L T GL Z plus high order terms in epsilon. Here epsilon L plus 1 multiplied by the integral between 0 and t of something that is bounded. Okay, so the displacement function in this case writes epsilon power to L times t multiplied by the average function of order L. Doing the same thing that we have done before, defining delta tu, but now as the displacement function divided by epsilon power to L in order to remove this coefficient, it's equal to t multiplied by GL z of plus order epsilon. And from here, the argument is the same. If we have a simple 0 of this function, then we can use the implicit function theorem in order to obtain a branch of periodic solutions from the simple 0. Okay, so summarizing, the averaging method provides a transformation that conjugates a non-autonomous periodic solution to another non-autonomous differential equation. Sorry, I said solution. It conjugates a non-autonomous differential equation to another non-autonomous differential equation, but the dependence on t only appears in the remainder. Okay, so what we have is that until order k of epsilon, the time t, the dependence on the time, does not appear here. Okay, so we can use that to expand in Taylor series the displacement function of this differential equation, and then to compute using the implicit function theorem branch of zeros of this differential equation of the displacement function. Okay, we could try another approach to study the periodic solutions, still using the displacement function. We could try to avoid the step of the averaging method, the conjugation step. Okay, we could try to expand the displacement function without conjugating the difference equation with an almost autonomous difference equation. We could try to skip this step, which is proveniente from the averaging theory. And this is what we call by Melnikov method, which consists in expand the Poincaré map or the time t map in power series of epsilon without the necessity, without the needing of doing transformation of coordinates. Okay, so the Melnikov method provides directly an expansion of the displacement function, and once we have, and the displacement function now is the displacement function of the standard form of the original difference equation. Recall that the standard form that we have worked before was the displacement function of the transformed equation. So the idea here is to extend the displacement function of the original equation directly without applying transformation of coordinates. If we have this expansion, then the same result as before holds. What I mean, denote f0 equals 0 and let L be the index of the first coefficient in this expansion that is distinct from 0. Okay, so let L be an integer between 1 and k, satisfying f0 up to fl minus 1 equals 0, and fl is not identically 0. Assume that z star is a point in the domain such that is a simple 0 of fl. Then, for epsilon sufficiently small, the difference equation 1 admits a unique t-periodic solution phi t epsilon converging to the constant function z star as epsilon goes to 0. I'm not going to prove this result here because it's exactly the same proof that we have here. Because here what we obtained was an expansion of the displacement function, but for another difference equation. Here I'm assuming that we already have the displacement function of the original difference equation. We already have this expansion, okay? I'm assuming that. An important remark that I would like to stress here, which is also true for the previous case, is that under this assumption, if fl of z is distinct from 0 for some z in the domain, then the differential equation 1 does not admit periodic solutions converging to z. Okay, so we can investigate also the regions of our system which does not have periodic solutions. And this is true because if we have a periodic solution, for instance, let's call t epsilon, then we can consider the initial condition. The initial condition, which depends of epsilon, is equal to 0 epsilon. And we know and suppose that it converges to z when epsilon goes to 0. We know that the displacement function applied in this initial condition is identically 0 because it's the initial condition of a periodic solution for every epsilon. Okay, so when I look at the expression, the Taylor series of the displacement function, I know that the coefficients, since it's true for every epsilon, the coefficients also have to be 0. Then it implies that fl of z epsilon is 0 for epsilon is small. And take the limit, we have that fl of z is equal to 0. So if fl of z is distinct from 0, then does not have, then the difference equation does not have periodic solutions converging to this point. Okay, this is a remark, a simple remark that also is true for the previous theorem. Okay, so taking into account this theorem, we say that if those functions fi are bifurcation functions because it's controlling the bifurcation of periodic solutions. Okay, and the expression, the formula for these bifurcations functions are given by the following result. Actually, fi of z is equal a function y I t z divided by e factorial, where these functions here, y, I, are given by the following lemma. Okay, so the idea here, it's very clear what I'm doing. Those functions are just the coefficients or the derivatives of the solution for epsilon equals 0. So note that y I of t z is equal the I derivative of x with respect to epsilon computed at t z 0. Okay, and we have a nice formula for this expansion. So y1 of tz is equal to the integral between 0 and t of the first order of our standard form, f1. And for higher orders, yi, we have this expression, which is a recursive formula for this function. So it's the integral between 0 and t of e factorial multiplied by fi plus a sum. I'm not going to the details of this expression, but it's a sum of the derivative of fi minus j, an m derivative of this function multiplied by the Bell partial polynomials. Okay, so this is a special polynomials which we have implemented, for instance, in Maple and Mathematica, partial Bell polynomials of the previous y's. Okay, so here we have yi, and this, and here we have y1 up to yj minus m plus 1. And if we look at to the extreme of the sums, we see that it's at most I minus 1. Okay, so this is a recursive formula. At the end of these notes, I have included the mathematical algorithm for implementing these and obtain at least formally the formula for the average functions of any order. Okay, so this is the Bell partial polynomials. I'm not going to explain the Bell polynomials here, but it's a simple expression. And here we have another note about the higher order derivatives of this function, which has to be seen as a multivalued map applied to a product of vectors. Okay. Well, okay. So when we compute the first order bifurcation function f1, we see that this is equal to the integral between 0 and capital T, the period, of f1 as z. It's just to apply this formula. And this is actually t multiplied by the first order stroboscopic average function. Okay, so it's usual to call this function is usually called by average function domain in the research literature. You can find it being called by average function. However, it's also called by Poincaré, Poincaré, and Melnikov functions, or just Melnikov functions, because it's a kind of Melnikov method which allows to expand the Poincaré map in Taylor series. Okay, this can be easily computed formally, at least if you substitute the the expression of the difference equation you're working, then it can be hard to compute. But formally, it's easy to be computed. You can have the expressions. Okay, so in order to prove this lemma 12, in order to prove lemma 12, the idea is to use the Fadibrands formula for higher derivatives of composition of functions. This is the formula. Okay, I'm taking the L derivative of G composed with H, and the Fadibrands formula says that it's a sum of higher derivatives of J composed with H multiplied by partial Bell polynomials on the derivatives of H. Okay, so this is the formula. This is where the Bell's polynomials are coming from, and what I'm going to do is apply this formula in order to have the expressions for the bifurcation functions, okay, and average functions too. So again, using the integral characterization of a solution of a difference equation, xtz epsilon is equal to the initial condition plus the integral of the right-hand side of the difference equation evaluated the solution. Since our difference equation has a sum, we can commute the sum with the integral. This is what I'm writing here. Okay, so in order to use in order to expand, what I want to do is expand this expression in powers of epsilon. Here we have some powers of epsilon. However, epsilon also appears here in this composition. Then we have to expand this function in power series of epsilon. And this is why we are going to need the Fadibrands formula. So this is what I'm doing here. Fitz dxtz epsilon is equal, this function for epsilon equals 0, plus the sum of j equal 1 unto some order of epsilon power to j divided by j factorial multiplied by the derivative, the j derivative of this composition on epsilon for epsilon equals 0. So for this expression, I'm going to use the Fadibrands formula. We know that this derivative, this higher derivative, is equal to the m derivative of fi multiplied by the partial Bell polynomials computed at the derivative of this function. And I'm calling these derivatives by yj. Okay? So I think that I'm going to skip some computations, because now what we have to do is to manipulate those expressions in order to obtain the coefficients of epsilon, because we have epsilon here. When we expand these terms in power series of epsilon, we have some epsilons here, then those epsilons multiply themselves. Something's not right. Okay. Then we obtain epsilon power to j plus 1. Then we have just to call this power, this exponent, by I. We made a change of index in those sums, and doing the manipulations, we obtain our recursive formula for the functions yi's. Okay? And this completes the proof of lemma 12. Okay, so now what we have is two sequences of functions, gi's and fi's. One of them are given by performing transformations of coordinates, the averaging method, and the other one is obtained just by expanding the time t map in power series of epsilon. And both series of functions are given the same informations, are providing informations on the bifurcation of periodic solutions of the original difference equation. So it's natural to ask if first, are they the same? We know that they're not the same because f1 is equal to t multiplied by g1. So perhaps every other function, higher orders, no, fi would be t multiplied by gy. We could ask that, but it's not true. So is there any relation between these two sequences of function which are obtained by distinct methods, but are providing the same information about the bifurcation of periodic solutions? So the answer is yes. We can develop a general recursive formula which links the functions gi's with the functions fi's. Okay, so we already have a recursive formula for computing the functions fi. So assuming that we already know that those expressions, then we can obtain a recursive formula for the stroboscopic average functions. Okay, and this formula I'm given here. I'm not going to explain this with much detail, but it's connecting these two definitions, these two kind of bifurcation functions. The first one we have already seen, g1 is just f1 divided by the period, and the other ones, for instance, gi is equal fi divided by t, but I have to subtract another function here. Okay, and in order to compute this function, we also have to compute this other sequence of functions. But note here that these functions y I tilde are always polynomial in the variable t. Okay, so this integral can always be done. It's not like the formula before here, that I am computing functions that I do not have much information about a priori. So here we can always compute this integral because this function will always be polynomial in the variable t. Okay, and this is also a recursively formula. So we can compute g1 have f1. After we computed g1, we compute y1 tilde, and have computed y1 tilde, we can compute it g2, because this expression depends only on g1 and y1, and so on. Okay. Applying this formula, we can compute the second order stroboscopic average function g2. Okay, and taking this theorem into account, we have some nice consequences. These have already been obtained before for planar systems. Okay, so it's a direct consequence of this general theorem. So denote f0 equals g0 equals 0, and let L be an integer between 1 and k. If either one of these two conditions hold, that is, if f1 up to fl minus 1 is equal to 0, or g1 up to gl minus 1 is equal to 0, then fi is equal to t multiplied by gi for every I between 1 and L. So actually what's happening here is the following. If this sequence of functions vanishes, then this sequence of function also vanished. And the next one, FL, coincides with T times GL. Okay. Analogously, if this sequence of functions vanishes, then this other sequence of function also vanishes, and also the next one coincides, but for a factor T, up to a factor T. Okay. So this is a first consequence, and another consequence is that we can come back for the averaging-like result about conjugation of differential equation, but now using the Munich function FL. So let L be the index of the first non-vanishing averaged function. Then there exists a t-periodic near-identity transformation X, U equal U T C epsilon, satisfying this stroboscopic condition such that the original difference equation, the first one I have introduced, is transformed into this differential equation. And now what we have here is the average function provided by the Munich method. Okay? This is why, because in these conditions, it's equal to GL of C. Okay, so here I provide.
Sorry, Douglas. Before to present the algorithm, I have two questions. In Formula 22, the natural way to write the G's is directly as a function of F's. It's easy to do the transformations directly, or maybe the recursive object will be very strange to write 22 directly in F.
But how can we do that? Because GI is given recursively, and it also depends of the others GI. So if J, for instance,
I understand, but as in remark 15th, you wrote directly, you have written directly G2
oh, yes.
directly in terms of F's. It's quite natural to write.
Yes. You can, if you can solve this. I didn't try to solve it, and I don't know if we can do that. But if you solve this recursive formula, then DI is a function of the F's and only of the F's. But I don't know if you can do that. You can solve, but it's true. Exists in a function such that DI of Z is equal F of F1, F2, Fi.
And the second thing is lemma 12 provides a very nice result because you have things. The lemma says that you have an explicit way, but this is strange because everybody knows that to pass to order 2 usually is very difficult. Here you avoid the problem because you just are writing in a compact way. But of course, you can only write explicit expressions in very special perturbations, and you pass very, very fast to this part. No? Maybe in the examples we will see.
Yes. I comment that it's easy to have formally the formulae for Y's, but it may be very hard to compute it if you have explicitly the difference equation that you're working. It's usually very hard, but I agree with you. Okay, so now just comment that in these lecture notes you can find the algorithm for computing both bifurcation functions, the Fi's and GI's. I'm not going to explain the algorithm, but it's a mathematical algorithm. You can just copy it, paste in a mathematical notebook, and it should work. Okay, but taking into account the comment of Joan Torregrossa, this is an algorithm that allows you to compute formally the formula of the average functions. You can obtain, for instance, here I'm providing the first 5 ones, but it is an integral. Sorry. But it's an integral of a very specific function, and it can be done in a very specific examples. It's usually very hard to explicitly compute these integrals. But if you want to have the formula, then this algorithm provides the formula. But to compute and to apply the formula in some concrete examples, it's a very difficult task. Okay, so I think that's enough for today.
Okay, thank you, Douglas. Yeah, some questions, comments? Nope. So, Douglas, thank you for your talk.
Thank you very much, and see
you later.
Yes, thank you.